Now I want to talk about another flavor of gradient descent that, at least these days, is used almost exclusively over the kind of vanilla gradient descent that I just showed you. And that is stochastic gradient descent. So stochastic gradient descent applies in the case where our log likelihood function is defined as follows. So here's our log likelihood function, and in the case where our log likelihood is, or where our likelihood is a product of many independent examples, our log likelihood turns into a sum over a bunch of likelihood terms over each example separately. So notice that we have this likelihood term L over y n and xn. And we could more simply just write it like this, where we have a likelihood function n for each example. So previously, we've been calculating the gradient over this entire log likelihood function, that is, over all of these data examples together. But the key insight of stochastic gradient descent is that if we choose some batch bt, where bt is a subset of our examples 1 to n, if we instead compute our gradient over just that subset, so that is, we compute our gradient to be the sum over the derivative of these log likelihoods just for the batch, that gradient we get is approximately equal to the actual gradient. And that's a huge benefit because let's say we have, let's use as just a simple example, let's imagine that each of our examples is repeated 10 times in our training set. And we choose our batch, and our batch happens to include just one out of each of those 10 repeated examples. So in that case, our gradient is the same as what we would get using batch gradient descent using the full data set, and our updates take 1/10 the time. So our overall optimization is going to take 1/10 the time. Now, of course, generally our gradients will not be exactly the same as the gradient we'd get from batch gradient descent, but often it's quite close. And because those updates are so much faster to compute, even though the gradient we use is slightly less precise, the algorithm as a whole, the optimization as a whole, ends up going much faster. And in fact, you can push that to the extreme. So in general, and you can prove some properties about this, we're not going to do that, but in many cases, the fastest thing to do, in fact, is to use batch sizes of 1. That's going to give you a much more noisy gradient. That is, the gradient is going to be much farther from the true gradient, but because each update is we can calculate so quickly, we'll end up at an optimum much faster than we would with using full batch gradient descent or even mini batch gradient descent, where we use some moderate sized subsets. And in fact, for problems where computation is a significant concern, stochastic gradient descent is almost always preferable to batch gradient descent. So for any kind of, for example, deep learning or sort of large-scale machine learning where a gradient-based method is used, it's almost always stochastic gradient descent that's used. By the way, a note on the name. So why stochastic? So stochastic refers to randomness, and random in the sense that our gradient is not the exact gradient, but rather some approximation of the gradient with some randomness. So in fact, there are other types of stochastic gradient descent that don't apply in this finite sum set. For example, if perhaps you're getting some noisy estimate from a real sensor and that's informing your gradient descent, you might still call that stochastic gradient descent because there's some randomness generated by that real world system that's influencing your gradient at each iteration. But generally when people say the word stochastic gradient descent, they're referring to this case where we're using mini batches or batch size of 1 for a kind of finite sum example-based gradient descent. So it's worth talking a little bit about why gradient descent is useful. And let's try to get a bit of intuition for it, and let's look at it a couple of ways. So the first thing is to realize that, in fact, what we generally want is not necessarily to optimize the log likelihood of our particular training data set, although that's what we have. So what we're really doing here is we're calculating the expectation with respect to d of our log likelihood function. That's just another way of writing what I've written here. What we perhaps would rather compute, or what we're truly trying to optimize, is the expectation over sort of the true generative distribution of our examples x and y. So what we're really trying to do is we're trying to optimize this model over all of the examples that it could possibly see, and just we have some limited training set of this. Okay, so why does that observation help us realize why stochastic gradient is useful? So the reason is that we have to come to terms with the fact that we're always doing mini batch gradient descent in some sense, because even if we're using the entire training data set we have access to, that is some mini batch of all the examples that we could possibly see. So now that we realize that we must do mini batch gradient descent in some sense, then why should we choose a particular batch size over another? So why is a larger batch size better? Well, it's going to give us a more precise estimate of the gradient. Why is a smaller batch size better? Because it's going to give us a faster computation of the gradient. So which do we want? Faster or more precise? Well, imagine the case where we're in our optimization and we are trying to compute a gradient. So an issue with batch gradient descent is we might do a ton of optimization or a ton of computation in order to compute our gradient at a given step. We have to, if we're doing batch gradient descent, we have to go over our entire training set and we have to compute this very precisely. But that gradient is going to end up changing pretty soon. So once we get to here, our gradient is going to change because now we're at a different spot in our likelihood landscape. So why spend all that time computing the gradient from this step, where if we just did a couple of sloppy updates, we could get to a spot most likely that's going to end up being sort of more relevant, in the sense that because we've ended up closer to the optimum, we have a derivative that points us more precisely towards it, rather than kind of this spot that we happen to get initialized into. So that's the reason for this trade-off of precision of the gradient versus speed of computation, because our stochastic step will generally put us closer to the optimum. We would rather update quickly and end up with an update which will let us in the next iteration give kind of a more informed computation of the gradient. We'd rather do that than very carefully compute the gradient at this step, which will very soon be out of date because the parameters that we're updating are going to change. So that's kind of one way of getting intuition for why stochastic gradient descent is useful. One more is just that why should we let the amount of data that we happen to have tell us how big or how precisely we should compute our gradient. We probably want to decide ahead of time how precise of a gradient we'd like, and then and we shouldn't be influenced by how much training data we happen to have, because that's something that's kind of given to us by the world. That's sort of not informed by the mathematics. That said, one reasonable answer to that question would be we want the most precise gradient updates possible. That turns out not to be what you want in practice. As I said, you generally want the fastest updates, not the most precise updates, which is why in general, what's used in practice and what in fact performs best is gradient updates with batch size of 1. That is, you look at just one example for each gradient update, or a very small number of examples, rather than batch gradient descent using all the examples. Okay, so that was a very long way of saying that in practice, for problems where computation is a concern, you almost always want to use stochastic gradient descent rather than batch gradient descent. And in fact, that's what's done in practice. Now, there are a couple of wrinkles that you have to deal with when using stochastic gradient descent, even more so than in batch gradient descent. And the first is that stochastic gradient descent, it's sometimes doesn't converge in cases where even batch gradient descent would. So generally in stochastic gradient descent, one must use a learning rate that decreases over iterations. So this is called making a learning rate schedule. That is some schedule by which the learning rate is going to decrease as you increase in iterations. And there's some common heuristics that I'm not going to write here, but that are given in the textbook that are commonly used for this. Another trick that's commonly used in practice is to do what's called iterate averaging. That is, at iteration t, instead of just using the update we showed before, we're going to compute our derivative from the average over some number of previous iterations. So we can write this here as this average over iterations, or equivalently, we can write it like this, where we use the current update plus some constant multiple of the previous updates. So this is going to greatly decrease the variance in our parameters, and generally will cause it to converge more often and converge more quickly when we're using stochastic gradient descent. There are a number of more sophisticated methods for decreasing the variance and improving the convergence rate of stochastic gradient descent. I think we won't have time to cover them in this course because they're a bit complex, but I highly encourage you to take a look at them in the textbook because they're very often used in practice, especially for today's kind of deep learning optimization, for which it's very common to use these sort of accelerations on stochastic gradient descent. And this often gives you sort of better convergence for these methods in practice. And they tend to have these goals of decreasing the variance in our updates, as well as using tricks such as momentum that we talked about for batch gradient descent to kind of speed up optimizations in some directions and slow it down in others.